Wonderful. Welcome, everybody. It's my pleasure to introduce Nicolas Berkouk, and today he will be telling us about sheaves as computable and stable topological descriptors of datasets.
Okay, so thank you very much, Henry, for the introduction. Thank you also, Sarah, for the organization. It's really nice to welcome the ATMCS talk in this online seminar. So my talk today will be, and actually the talk is kind of shared also with Francois, who will be talking after, will be to try to explicit some connections between sheaf theory on the one hand and persistence theory on the other end. So why would we want to do such a thing? Well, because each of the theory has benefits and disadvantages, and maybe we can success in enjoying the best of both worlds. Okay, so the benefits of sheaf theory are that it is a really powerful theoretical framework. Okay, but it lacks being easily computable. It is a very theoretical language. On the other hand, persistent theory has been precisely designed to be easily put into a computer, but in some sense, it can seem at first sight a bit naive from the algebraic topological point of view. Okay, so during this talk, we will try to set up connections, precise, explicit connections between the two theories in this aim. Okay, so my talk will be in the setting over R, where both theories enjoy decomposition theorems. And so the main point will be to try to explicit the connections between the decomposition, so between the descriptors that we have in each theory. And the talk of Francois will be at a higher level, where we will set up connections, but at a purely categorical level. Okay, so I will really be very, very quick and fast on definitions because of the length of the talk. Okay, but all the details are available in our papers. Okay, I will give the reference at the end of the talk. So what is a sheaf? So really quickly, a quick introduction. So we want to start with the topological space X, and we can consider the category of its open subsets. Okay, so it's a category which has objects which are open subsets, and we put one arrow between two open subsets along the inclusions. Okay, and so a pre-sheaf of k vector spaces on X will just be a functor from the opposite category of open subset of X to the category of k vector spaces. So what it means that to each open set, we associate a vector space, and to each inclusion of open sets, we have a restriction morphism from the bigger open set to the smaller one. Okay, and so now we don't want to consider all of those functors. We want to consider those ones that satisfy a certain local to global property, which means that we can actually extend local information to global information. So how do we formalize this? This is thanks to what we call the gluing axiom. So we consider an open set of X and an open covering of U, which is stable under X intersections. And we will say that F satisfies the gluing axiom with respect to the covering if the value of F on the open subset U can be uniquely determined canonically as the limit of F on the open covering. Okay, and so we will say that F is a sheaf if it satisfies the gluing axiom for every open set, and every open covering of each open set. So there already has been some work on persistence and sheaves. So Justin Curry, in his thesis, which is called Sheaves, Co-sheaves, and Applications, made the first connections between persistence and sheaves. And there is also another very important work by Masaki Kashiwara and Pierre Schapira, which is called Persistent Homology and Microlocal Sheaf Theory, which was published in 2018. And we will work in the setting of Kashiwara and Schapira. So they are working in the derived category, and for a lot of reasons, this is the setting in which sheaf theory takes its full strength. Okay, so and this was only partially done in the thesis of Justin Curry. So this is why we choose to work in this setting. So what is the derived category? So this is very ambitious to try to describe what is the construction of the derived category in one slide, but I will try to do it. So basically, you start with an abelian category. So think maybe of the category of modules over a ring, a commutative ring. And you want to build a category in which you can do computations of homological algebra. And so to do so, you start by building the category of bounded. So I will just express the bounded derived category. So you consider the category of bounded chain complexes over A. Okay, and then in this category, you look at morphism between chain complexes, which induces isomorphism at the level of homology. And we will call those chain morphisms quasi-isomorphisms. And so what we do to build the derived category, we start with the category of chain complexes, and then we formally invert all of the quasi-isomorphism. Okay, so there is a rigorous process to build a category like this, but I absolutely don't have the time to express it now. Okay, and so the important property of the derived category is that in the derived category, quasi-isomorphisms become isomorphisms. So now I will try to explain you very quickly what has been introduced by Kashiwara and Schapira in their paper. So basically, they have defined a kind of interleaving distance for sheaves, okay, which is based on convolution of sheaves. So the setting is that we are looking at sheaves on a finite dimensional real vector space that we equip with a norm, okay, and we look at the addition map here. So to x and y, we associate x plus y, okay? And I will use this notation for the bounded derived category of sheaves on V, okay? And so there is an operation which is called the convolution for sheaves, which is this formula. So if you know the formalism of Grothendieck operation for sheaves, you're lucky. If not, just remember that we have an operation of sheaves, which we call the convolution, and that has the same formal property, for instance, than a tensor product. So we will not be interested in taking the convolution with all of the sheaves. We will restrict our case to a certain family of sheaves, okay? So given epsilon in R, we define so k epsilon to be, if epsilon is positive, the constant sheaves over the closed ball of radius epsilon. And if epsilon is a negative, then it's the constant sheaf over the open ball of radius epsilon with a given shift in grading, okay? And so here you must think of taking convolution with k epsilon as playing the same role than the shift functor for persistence module, okay? So in particular, it satisfies that taking the convolution with k epsilon and taking the convolution with k epsilon prime is the same thing as taking the convolution with epsilon plus epsilon prime, okay? And also taking the convolution with k0 is like doing nothing. Also in persistence, you also have a map, a canonical transformation from a persistence module to its shifted persistence module, okay? And here we have exactly the same property, but for sheaves, the arrows are going in the other direction, okay? So if I have epsilon prime that is greater than epsilon, then I have a canonical arrow from epsilon prime, from f convolution with k epsilon prime to F convolution with k epsilon. Okay, and so in the special case where here I just put epsilon equals 0, so this is isomorphic to F, and I get a canonical arrow here from F k epsilon prime to F. So now I have all the ingredients to define a kind of interleaving distance for sheaves. Okay, so I will say that F and J are epsilon interleaved if I have the usual interleaving diagram, but with all the arrow reversed because we are working with sheaves. Okay, so in particular, it is the data of a morphism from F k epsilon to J and a morphism from J k epsilon to F, such that it factorizes the canonical morphisms of F and G, of length to epsilon. Okay, and so I will use this notation to say that F and G are epsilon interleaved. So now we can define, exactly like for persistence module, a distance from those interleaving. And so we define the convolution distance between F and G to be the infimum of the epsilon, such that F and G are epsilon interleaved. So now this distance satisfies the same formal properties than the interleaving distance for persistence module. So it is indeed an extended pseudometric on the derived category of sheaves on V. And it satisfies also a stability theorem. So here, remember that, so when you take the two persistence, so when you take the persistence module associated to one function and to another function on the same space, you know that this is the stability theorem. Your two persistence module won't be further apart for the interleaving distance than the supremum of the difference of the two functions they are built from. So here it's exactly the same thing, but we have to consider what does it mean for sheaves to take the sheaf associated to a function, okay? And so there is this operation which is called the derived push forward, which is really something standard in sheaf theory. And so if you take one sheaf and you push it forward with respect to one function and another function, then you know that for the convolution distance, you can't get further apart than the distance between the two functions. Okay, so this setting really satisfies the same formal properties than persistence module over R. And so now, yeah, so so this is, so I was working here with a vector space of arbitrary dimension. Now I will restrict myself to sheaves on R. And if I ask my sheaf to be constructible, so it is a kind of tameness assumption, then I also have a decomposition theorem, which is exactly formally the same thing than the Crowley-Beauvais theorem for persistence module, which states that a constructible sheaf on R is essentially uniquely isomorphic to a direct sum of sheaves that are constant over intervals of R. So I can define for a given sheaf a barcode. So this was for a sheaf, real decomposition theorem for real sheaves, okay? So now when I go to the derived category, this implies, so this is also some homological algebra machinery, that any complex, so this is a chain complex of sheaves, and in the derived category, it will be isomorphic if I look at constructible sheaves on R. To its graded direct sum of cohomology objects. Okay, so this is a chain complex, but this is a sheaf, really a sheaf. Okay, and so this is by assumption here a constructible sheaf. Okay, so this admits a barcode. So here I see that for an object in the derived category, I also have a notion of barcode by taking in for each degree recording the barcode of the sheaf. Okay, so it means that I can define the graded barcode of a constructible sheaf over R to be this sequence of barcodes. Okay. So now a question that could be natural is, do I have a notion of isometry theorem in this context? So can I compute the convolution distance between two sheaves as a matching distance between their barcodes. So here I have an example, I give you an example, so believe me on the computations. So I take the constant sheaf on the circle in both cases, and I will push it forward onto R with respect to two different functions. So here I take the first coordinate projections, and here I take the contraction onto 0, okay? And so if I take, so this is the derived push forward of the constant shifts on S1, sorry. And so in degree 0, the barcode looks like this. So you have two bars, one closed, one open one, and you have nothing in degree 1. And here in degree 0, you have just 1 point here and 1 point here. And so by the stability theorem, as the sup norm between f and g is equal to 1, I know that the convolution distance between those two sheaves must be bounded by 1. So can I find here a 1 matching between those two graded barcodes? And so here I see that it is, so the answer is that to do so, I have to allow the matchings between this open bar and this point, okay? Because the point here, it is not like in persistence. The point here is at distance, it is at infinite distance from the 0 sheaf, okay? So I can define graded matching, epsilon graded matching between graded barcodes, okay? And so our result with Gregory-Gino is that the convolution distance is actually equal to the bottleneck distance between the graded barcodes between F and G, okay? So now we know that formally the context of sheaves has the same property than persistence. We know that if we know how to compute the graded barcodes between sheaves, then we can compute the distance as a matching distance. There remains one question: can we actually compute the graded barcodes between sheaves, the graded barcode of a sheaf? And so, sorry, to do so, we will actually compare sheaves on R with persistence module over delta plus between being, sorry, this poset. So it is the indexing poset of open bounded intervals between R, okay? And so we have made the link between, so I will maybe skip a bit. Made a link with Gregory-Gino also and Steve Udo, sorry, it's supposed to be Odi. So this is the level, the ice level. So you start, sorry, with a function on a nice topological space to R, okay? And so this notation stands for the level set, the ice level set persistence module associated to a function f, okay? And so we have proved with Gregory and Steve that there is a functorial bijections between the collection of barcodes of level set persistence and the graded barcode of the derived push forward of the constant sheaf on X, okay, which induces an isometry for each of the bottleneck distance here and here, okay? So this means that it is actually possible to compute the sheaf barcode from the level set persistence barcode. And this is a good news because software already exists. For instance, there is a Dionysus that has been implemented by Dmitry Morozov. And on the other hand, it also gives a deeper interpretation of the level set barcode, okay? And so, yeah, so I give you here so the reference of, if you're interested into the details of what I said. So the first paper was a derived isometry theorem for constructible sheaves on R with Gregory-Gino. And the second one is level set persistence and sheaf theory with Gregory and Steve Udo. And I thank you for your attention.
Thank you so much, Nicolas, for the wonderful talk. Everybody, let's briefly unmute ourselves and then clap, and then we'll mute ourselves again. All right, what questions do we have for Nicolas? Nicolas, so let me start with the question. So when you were talking about matchings, you had one case where the circle is being projected to the real line and one case where it's being mapped to the origin. And you said that you matched one of the bars on the left in H0 with the point for H1 on the right. Why couldn't you just match that that bar with the I don't know, sort of like an empty bar, a bar sort of corresponding to the diagonal in the language?
Because you must define the matching with respect to the convolution distance. So, for instance, an epsilon matching between two bars must be such that each, when you look at the associated sheaves, they are at epsilon convolution distance. Okay,
I see.
And so here the behavior is really different than for persistence. And so this, when you will take the epsilon convolution, for instance, of this one, it will shrink and then go to 0. And when it goes to 0, it will pop up in 1 degree above. Okay,
I see.
So you really have a derived behaviors, and you must allow matching across degree, because otherwise there is no matching that respects degree between those two barcodes.
Huh. That's really nice. It's a lot more structure. So there's a chatted question from Vadim, and he says, what sheaf F should one usually choose to associate a derived sheaf to the function h from x to the reals? I don't know if you can see the chat window, Nicolas. You might have to stop sharing your screen. He says, this question is linked to the equation DC, or the convolution distance between RH1 and F and RH2 of F.
One usually choose to associate a derived shift. Yeah, so you take the derived push forward of, so you take the derived push forward of the constant sheaf on X. So the usual case, the case of persistence. So when we are looking at persistence module, roughly what this theorem says is that it's the same thing as looking as the derived push forward by F of the constant sheaf on X. But what's interesting here is that you can look at barcode of very different sheaves here, whereas in persistence it's not obvious how to do this, how to do a more refined constructions.
He says, perfect, thanks.